Hello, welcome back. We've looked at systems so far that have been square. 0, 1, or infinitely many solutions. Most of the time, we have either more equations than variables, or more variables than we do equations. And so the Gaussian elimination process takes place in exactly the same way, though it looks a little bit different. And I thought it might be useful for us to take a look at a couple of examples of those. So when we say m by n, all we're saying here is that the number of rows, in this case, if we have equations, so let's say we have a11 x1 plus a11 x2 plus and so on, all the way up to we're going to have n variables. So we'll have our final variable will be the nth variable. Remember, this is the number of equations. This is the number of variables here. And so this will be a1n. It's the first row nth variable coefficient. And this is going to equal some constant. And then we'll have, in a similar sense, a21x1 plus all the way down to a2n xn equals c2. But we're going to have m of these equations. So down here we'll have a m1, that's the mth, it's kind of a weird thing to say, the mth equation, and all the way up to a mth equation, nth variable, xn equals, and then we'll just say some final constant there. So if you look at this, you see that we have m equations, and we have a variable here, we have a variable here, we have a variable all the way down the line. So we are going to have n variables. And so this is what we're going to call an m by n system. Now, as one example, we could end up with situations that look like this. 1, 0, 0, let's say 0, 2, and then 0, 0, 1, 1, 3. Let me actually take back a couple of those. 0, we'll say, 0, 0, 1, 1, 3. And we end up with a funny statement like this. In this case, maybe we have x1, x2, x3, x4, and then our constant over here. And we want to know how to go about interpreting this solution. So it appears that the first equation tells us that if this were our reduced row echelon form, and notice that it's not possible to have our coefficients along the diagonals. There aren't enough diagonals from left to right for us to have that nice standard reduced row echelon form, or that standard Gaussian form. In the next video, you'll see something about reduced row echelon form and what I mean there. So basically, x2, the x2 column, does not have a row ever in which there is a leading 1. The only other variable that has a leading 1 in one of the rows is x3. So let's pay attention to that for a second. The first row says, well, x1 equals 2. Well, there we go. That looks good. The second row says that x3 plus x4 has to equal 3. That's the constraint that we are placing on this system. Now, x2, there's no constraint at all on x2. So because x2 has a 0 coefficient, if you think about it this way, I could plug in any number I want for x2, right? x2 could be 1,000 or 500 or 1,000,000. And it would not matter because it wouldn't affect the fact that x1 is still equal to 2 and that x3 plus x4 has to equal 3. So x2 in this case is a free variable. And you'll also notice that x2 is one of two variables that does not have a leading 1 in any of the rows as you look down. x4 is also such that there is no row in which x4 has the first non-zero value. The first non-zero value in row 2 appears in the x3 column. So this is going to be a quick way for us to tell what the free variables are right off the bat. We can also talk about the intuition here in a moment. So all we know so far is that x1 has to equal 2, x2 is some free variable, and without, again, we could use any letter we want other than x sub 1 through x sub 4, so I'll call this value c. All right, so we know that x1 has to equal 2. We know that x2 can be anything we want it to be. Our solution vector, which we would write x1, x2, x3, x4, those values so far are going to take on 2 for x1, x2 is going to be some free variable, and we're going to work on x3 and x4. So the only constraint that this second equation gives us is it just says that whatever x3 and x4 are, they have to add up to be 3. So I look through my list here and I say, well, what does x4 have to be? And there's no information on it. We don't have any equation at all that tells us what x4 must be. Similarly, we don't have an equation that says x3 must be 5. It's just one equation that says x3 plus x4 is equal to 3. So, in the first row, in the second row, we notice that x3 was the variable with the leading 1. So, we could say that x3 is a free variable, but typically, the variable that has a leading 1 in one of the rows, we let that variable be determined by the other one. So, x3 equals 4. x3 equals 4 is the same thing as saying x3 is equal to 3 minus x4. So basically, if you take away x4 from 3, that's what x3 has to be so that they add up together to produce 3. Now, since there's no constraint on x4, x4 is going to also be some free value. It could be anything we want to be. But once we know what x4 is, for example, if x4 is 1, then x3 has to be 2. If x4 is 5, then x3 has to be negative 2. So x4 is going to be some other value. You could call it s, t, whatever you want. It just can't be c again because it doesn't have to be the same as the value of x2. We don't have a statement in here saying that x4 equals x2. So x4 is any variable, any value that we want. And just over here off to the side, I'll say c and d, and this symbol here just means are elements of, or belong to, or are members of the real numbers. So c and d are real numbers. That's all this statement means. So we have our solutions. And the last thing we need to do is say x3 equals 3 minus that value of d. So we have x3, we know what x4 is, we know what x2 is, and we know what x1 is. So x4 is going to be d, x3 is going to be 3 minus d, and any value of c and d that we pick will work for this vector, will work for this system. It will make sure that x3 and x4 add up to 3, and it will make sure that x1 is equal to 2. Great, let's go ahead and apply this now. Let's look at a system that has 3 linear equations in 2 dimensions, and if we take a look at the system in graphical space, we see that they don't all intersect at a common point. Any pair of them intersects, but not at the same location. So I'm going to be a little bit careful here because this equation at the top is not written in the form that I need to be able to put it into a augmented matrix. So I'm going to add 2y to the left, get x plus 2y equals 6. I'll rearrange this while I'm at it. 2x plus y equals 4. 3x plus 2y equals 9. And so my matrix is going to be 1, 2, 6, 2, 1, 4, 3, 2, 9. And I think I'm good. I like the order of this. I already see I have a 1 here. I'm now going to use that to help me eliminate the 2 and to eliminate the 3. Now I'm going to do something kind of uncustomary. I'm going to go ahead and do 2 operations in 1. Oh, by the way, this is a 3 by 2 system. 3 by 2 system. It's 3 by 2 system. It's a 3 by 3 matrix, but it has 3 equations in 2 variables. All right, so I'm going to go ahead and do 2 operations. I'm going to take negative 2 times row 1, add it to row 2, leave the result in row 2. Negative 3 times row 1, add it to row 3, leave the result in row 3. So that's going to give me 1, 2, 6. Here I'll have negative 2 times 1 plus 2. This will be negative 3. Negative 2 times 6 plus 4 is negative 8. And down here, negative 3 times row 1 added to row 3 will give me 0. This will be negative 4. And negative 3 times 6 is negative 18, plus 9 is negative 9. There we go. Okay, so it looks like we're getting closer. We've eliminated the zeros here. I'm now going to focus on making this a 1 right here. So I'm going to go ahead and perform the operation negative 1/3 row 2 into row 2. That's going to leave me with 1, 2, 6, 0, 1, and this will be 8/3. And down on the bottom I'll have 0, negative 4, negative 4, negative 9. Awesome. So now we're ready to perform another row operation. I'm going to use this 1 here now to cancel out this negative 4. So I'll take 4 times row 2, add it to row 3, leave it in row 3. If I do that, I'll get 1, 2, 6, 0, 1, 8/3. And then, let's see, 0, 0. And I don't know what this exactly will come out to be, but I know this will be 4 times 8/3 is 32/3. 32/3 minus 9. And for all intents and purposes, we can go ahead and stop there. Because we see that in the third row, we're going to be reading the statement 0 equals 32/3 minus 9. And I don't know exactly what this comes out to at the top of my head, but that's not equal to 0 right there. We see it already in the graph. In the graph, we see that there are no solutions to this system. In the Gaussian process, we've been able to determine that 0 cannot equal a non-zero value. Therefore, our system is said to have no solutions. So you see the process is very, very similar. It stays intact. Let's do it for a system of 2 equations with 3 variables. So this is going to be a 2x3 system. 2 equations, 3 variables. By the way, if you have more equations than you do variables, you're oftentimes going to end up with no solution. Not always, but most of the time that does happen. If you have fewer equations than you do variables, then most of the time you're going to get infinitely many solutions. So that's just a good kind of bit of intuition there. And why is that the case? Well, if you're thinking about 2 planes with 3 variables, and those are going to be sheets of paper, and they can intersect along a straight line, or they could actually be the same plane, which is the case here. So I set up my system, negative 2, negative 1, 1, 1, negative 4, negative 2, 2, 2. And I like the arrangement of this. I'm going to go ahead and take negative 1/2 of row 1. Negative 1/2 of row 1, put it into row 1. So we proceed in much the same way. We want to make this a 1, we want to make this a 0. So this is now going to be 1, this is going to be plus 1/2, this is going to be negative 1/2, and negative 1/2. Second row is going to be, the second row is going to be the same because we haven't done anything to it yet. But now I'm going to go ahead and take 4 times row 1, add it to row 2, store the result in row 2. That's going to give me 1, 1/2, negative 1/2, negative 1/2. And 4 times 1 minus 4 is 0. 4 times 1/2 is 2, minus 2 is 0. 4 times negative 1/2 is negative 2, plus 2 is 0. Uh-oh. We're on the verge of maybe having no solution, but let's see. 4 times negative 1/2 is negative 2, plus 2 is 0. Whew, so we're good. We in fact have infinitely many solutions, and there's nothing else we can do here. The next step would be if there was a 1, if there was a non-zero value here, we would want to make that a 1 and then use it to cancel out the value above it. But we don't have that, so there's nothing we can pivot off of in the second row to change the first row. So we have to read off the final solution. We have x plus 1/2 y minus 1/2 z equals negative 1/2. And the second equation, of course, just reads 0 equals 0, which is not useful at all. Okay, so now we're ready to write our solution. But let's think about this for a moment. There's no equation in here that tells me what y has to be. So that means y is a free variable. Also, there's no equation in here that tells me what z has to be, so that's a free variable. meaning that I could pick any values for y and z that I want, and then x will have to kind of adjust itself mathematically to make sure that that statement remains true. So basically we have two undetermined values. If we plug in two of those undetermined values, the third one can be determined based off of previous two. If we only say one of these is a free variable, then we'll end up with a statement like x plus 1/2 y equals something, and that still is pending the value of y. The other way of looking at this, as in the first example that we looked at, is that in the first row, the x column has a 1 in it, a leading 1. So that means x is not going to be a free variable. In row 2, I have no leading 1s. There's no leading 1 there, no leading 1 there, no leading 1 there. Therefore, there's no other predetermined value for the other variables. So if I say something like y equals c, z equals d, we're going to assign these to some arbitrary values. C and d are both real numbers. Then based upon that, I can say that x plus 1/2 c minus 1/2 d equals negative 1/2. And moreover, I can write x equals negative 1/2 minus 1/2 c plus 1/2 d. I've got my value for y, I've got my value for z, I've got my value for x, and I'm ready to write my solution. X, y, z equals, so x is going to be this fractional expression here. Y is going to be c, and z is going to be d. So let's just do kind of an intuition check. Let's say c equals 1, d equals 2. Let's say no, c equals 2, d equals 4. So that means that the ordered triple that will work for these values will be, well, y has to be equal to 2, z has to be 4, and now x is going to be negative 1/2. Let's see, minus 1/2 of c, that's negative 1/2 minus 1 plus 2. Negative 1/2 minus 1 plus 2 is going to be negative 1/2 plus 2, which is 1.5 or 3/2. So let's just go ahead and check this into one of the equations. If I take negative 2 times 3/2, and what do we get there? We got 2 and 4 for y and z. So if I take negative 2 times 3/2, that's going to give me negative 3. Minus 2 is negative 5. And guys, this is what happens when you do things in your head. This should be 1/2. I did the math wrong here. So this should be 1/2, because I was seeing that it wasn't going to work out. So this is going to be not 3/2, but it's going to be 1/2 right there. So that's going to be a 1. So negative 2 times 1/2 is negative 1. Minus 2 is negative 3. Plus 4 is in fact 1. We could check it for the other equation and see that we also get 2 on the left-hand side. So this is just how we work with systems that are non-square. We just have to kind of progressively go through that process of Gaussian elimination. And in our next lesson, we're actually going to do it by using technology. So this portion of it is important to understand how this algorithm works, but our next up is to figure out how to do this with the technology that we have at hand.